In the film Armageddon, Bruce Willis saves the world from an asteroid, but if it wasn't for a mathematician, he wouldn't know it was coming in the first place. So today, we're going to talk to a mathematician who knows all about it. G'day, Philip, how are you?
Oh, hi, John. I'm good, thanks.
First question I have to ask you, obviously, is what are the chances of an asteroid hitting the Earth?
Good question. It depends on the size of the asteroid. So if we're just looking at something 100 metres across, the length of a rugby field, then you can expect we'll be hit maybe once every century on average. But if you're looking at something a kilometre across, then maybe over 1 million years we'll get hit several times in that 1 million years. So it's going to depend on the size.
Okay, so when was the last 50 to 100 metre asteroid?
Almost exactly a century. In fact, the centenary is going to be 2008. So 1908 in Siberia, an asteroid about that size didn't hit the Earth. It exploded several kilometres above it.
Okay.
And it flattened trees over about 2,000 square kilometres.
And if you were going to drop an asteroid, probably Siberia is not a bad place. There's not that many people, and
that's right. Yeah.
It's kind of, you know.
Yeah. You can imagine dropping an asteroid here in Auckland, 100 metres across. So the crater will be maybe a kilometre across, and everything would be flattened within 10 kilometres. So most of Auckland would disappear.
But what kind of warning will we get of something that big going to hit us?
Okay, in most cases, well, at the moment we don't know where all the asteroids are, but NASA's working on a program to find all the large asteroids. At the moment they're just going down to several hundred metres across. They're not trying to find the really small ones. So they figure by maybe 2015, 2020 they'll know where almost all the large asteroids are. And once they know that, then we can usually predict 10 or 15 years in advance, reasonably accurately. Not perfectly, but just reasonably accurately.
Okay.
So we would get some idea whether it was likely to hit, and then we can make further measurements.
Okay, so that gives us some sense of comfort. But so that's where the film got it a bit wrong, didn't they? Because they didn't have much time.
That's right.
And it was a kilometre or something.
Yeah, we would certainly know about that.
Yeah. And is there anything we can actually do?
Yeah, there are a number of things. Now, that's another thing the film got wrong. It suggested that you could blow an asteroid up. Now, an asteroid at 1 kilometre across with today's bombs, we've got no hope of blowing the asteroid apart. And even if we did, it would just expand and then probably flop back together again.
Okay.
Even 100 metres across, we're going to struggle to blow it apart. So the thing we have to do is deflect it from its orbit. And we have to do that over a number of years. So one way of doing that is to put a nuclear engine on the asteroid. So it's a bit like a rocket.
Yeah.
And the nuclear engine pushes in that direction, the asteroid will push in that direction. Not very far, and maybe 1 or 2 millimetres, but that accumulation of those millimetres will be enough to cause the asteroid to miss after 10 or 15 years. So we have to plan a long way ahead.
So the key, of course, is that you only have to change it, its direction by a small amount, and then we'll be fine.
We hope, that's right.
Yeah.
Because we don't know exactly where the asteroids are necessarily, and so the orbits we have at the moment are not perfect. So we'd have to be careful we didn't actually make the situation worse.
Yes, that's true. More recently, have there been any large ones that have come close?
Right, there have been a number that have come close, but I'd like to think into the future a little bit. There's one that's coming through in 2029, which has the sort of highest probability of hitting us, and that's about 350 metres across, so 3.5 rugby fields across. And it's expected to get about within 35,000 kilometres of the surface. So that's up where some of the satellites are. So it'll be quite an interesting sight. We won't see it from here in New Zealand, but they'll see it in Europe and Asia as it comes through. And then in 2036 it may come even closer, although it's hard to predict.
Okay, so we'd lose a few satellites at this stage, but nothing other than that.
No, there's still a chance that it could hit us. So there's about 1 chance in 30,000 that it will hit us.
So how do we get that information? I mean, because things change, don't they?
That's right, yeah. And it's such a complicated process because we've got all the planets interacting with one another, all the asteroids interacting with one another. So it's a challenging mathematical problem, a computational mathematics problem. So the first step is to write down a model of the solar system and all the forces that are there. And people do have models, but they're not perfect. There's still things that should be included, but they haven't been included. And then once you've got your model, it's too complicated to solve using algebra and calculus, so you use computer simulation. So you need good software and good methods, good algorithms, and then you solve it as accurately as you can, this model.
So this is the basis of computational mathematics. This is the sort of thing, the work that you'd end up doing. You could work for NASA.
That's right, yes.
Also, what about the robotic missions? Would that be involved in that as well?
That's right, because most of those are done by NASA. There's some done by China and Japan, the European Space Agency. but you're trying to work out your best orbit. You want to minimise the amount of fuel when you're sending a spacecraft up. And so that all involves computational mathematics, because once again, you can't solve the problem exactly. You have to make approximations. And they're really detailed models, and lots of computer time is used there.
Okay, so rover heads off to Mars, so he's at Mars now, isn't he? And when he's on his trip, do they have to make little corrections there as well?
That's right.
Different things happen?
Well, it's not so much different things happen, it's because they don't have an exact model of a solar system. So they know that after 3 months it'll be within 100 kilometres of a certain position, or 100 metres or whatever. So they have to include course corrections. And that raises an interesting situation. Some people think, the people who believe in conspiracy, that we're making these course corrections because there are aliens out there.
There's something out there after all.
That's right. Yeah. But it's just because we don't know exactly where or have a precise model. Yeah.
Well, what other jobs might you end up doing if you do computational mathematics?
Okay, well, another interesting one I have an interest in but haven't pursued is traffic engineering, and that's of relevance here in Auckland. So the idea is you devise a model, or write down a model of the traffic, and then you fine-tune it for a particular intersection or a rush hour, a different part of Auckland, and you run simulations, and you get some idea how the traffic is behaving and see if it agrees what actually happens in real life. And then you think about, well, maybe if I change the phasing on the traffic lights, for instance. There's been a proposal, and that actually has been implemented in places, of having traffic lights getting onto the motorway to try and avoid congestion. And so that's another interesting example. Another good example is in ecology or resource management. For instance, trying to work out the effects of pollution. Or when you have a storm and there's overflow of sewage in that, what sort of effect is that going to be? How can you minimise the effect of sewage when it goes out into the sea?
And all these have the base of computational mathematics.
Yes, because you can write down a mathematical model, but usually you can't solve it using algebra and calculus, so you have to use approximate techniques. And there are large problems. If you did it by pencil and paper, it might take you 20 years or something, whereas you can do it in a few minutes on a computer.
And of course there's a lot of commonality, isn't there? I mean, you look at the universe and Auckland's traffic, chaos theory, it happens in both of them, doesn't it?
That's right, yeah. So another project I've worked on is looking at galaxies interacting. Now, that's not going to help us put bread on the table, but it's an interesting problem to look at that.
Yeah, absolutely. And also, what about colonizing Mars? Do you think that's on the cards at all?
I would like to do that. We're certainly capable of doing it. I wouldn't want to go there myself, but I think within the next 50, 100 years we're capable of doing that. And so there's lots of things to optimise there. You've got, when the crew is going over, you want to minimise the exposure to radiation. You want to ensure they have some sort of gravitational field, so you have artificial gravity. And then when they get there, they have to worry about dust storms, and you have to worry about finding water. There's all sorts of situations to model. The mathematics can help a great deal there.
Okay, so there's lots of scope for employment in mathematics once we get to Mars.
Yeah.
Well, thanks very much for talking to us about all that, Philip.
Enjoyed it.
Really
Thanks.
appreciate it.
That's good.